Let's talk storage of fuels. This is chapter 3 of Tim Noakes's The Lore of Running, and part 2, storage of fuels. So storage of fuels, really talking about storage of fuels in the human body. But here I just have some pictures from a iron distance race. I walked around transition. I took some pictures of different setups where people have storage of fuel on their bikes. Or they may be getting storage of fuel from aid stations, or they may be carrying things like in this pocket for this runner. But lots of different storage potentials here on the top tube of the bike, in a bag that's placed on the top tube of the bike. This person actually has a schedule of what to do during the event. So where to eat, where to drink, and they've got the different notes on here. And then someone just used a hamburger for the bike bag, like toolbox. All right, so so lots of ways to store fuel during a race, but we're going to focus more on storage of fuel in the human body. So when in the human body, water accounts for up to 64% of total body weight. Of course, this is going to be based upon individuals and body composition, but we'll work through this. Fat is the largest energy store in the body. Fat is a very efficient way to store chemical energy. Remember, chemical energy, our energy pathways are designed to transform chemical energy to mechanical energy, or ATP. And then ATP is used to, in the sliding filament theory, of muscle contraction, generating a force, ultimately allowing for movement. So we're going to take chemical energy and transform it over to mechanical energy ultimately. Fat is a very efficient fuel that a very efficient way to store chemical energy. Carbohydrate stores in the body are relatively small. And if carbohydrates was the only fuel available during an endurance event like a marathon, the storage of that fuel would only last about 2 hours. Of course, that's different between people, but it's a rough number that we used in terms of the amount of carbohydrate that's stored in the body. We'll talk about that. And we saw that in chapter 1. You have carbohydrate in the liver, you have carbohydrate in the muscle, and the liver will release carbohydrate, glucose into the blood, and the blood delivers it to the muscle. All right, so this is an important figure. Make sure that you're comfortable with this figure from the chapter. And Noakes has 4 schematics here. Let's go through each one individually. This is the percent of weight of different organs. So we've got muscle at 37% of the weight. So if we weigh someone, I'll do an easy math. If someone weighs 100 pounds, this would be 37 pounds of muscle. 15% body fat, obviously this is your body composition. So if you step on your in-body scale or you do underwater weighing and you determine your body composition, this is a person who's 15% body fat. Some people may be higher than that, some people lower than that. Obviously, all these numbers are adjusted based upon your individual body composition. Bone is about 15% body weight for this person. Miscellaneous weight, other types of tissue, 10% skin, blood, 8% liver, brain, heart. Okay, so those are the relative weights of different organ in figure A. Figure B is percent of weight of different energy sources. So water is 83%, not really an energy source, but it is an important part that's going to be part of energy. Here we've got carbohydrates. It's only going to be 1.3% of energy availability in the human body, whereas fat is 15%. And again, that's by weight, okay? Now down here, we have percentage of total energy stores in grams of fat and carbohydrate. Adipose tissue fat, 87% of total body energy storage in grams. Liver glycogen, just 2%. Muscle glycogen, 6%. Muscle fat, remember fat can be in the muscle, 5%. Okay, so the important thing here is to understand fat is readily available as a chemical energy. Carbohydrate either in the liver or muscle, is a very small percentage of the energy stored in the body. That's important because ultimately we're going to be talking about what to eat during an event, and it may make sense to replenish carbohydrate stores before they're depleted. And there's not a lot of carbohydrate stored in the human body at any time. And the last figure, D, is just percent total body energy stores in kilojoules. So now it's just a relative amount. So here now, just emphasizing the same point I've been making here, fat is a big percentage of the energy available in the human body, 91% for someone who's 15% body count. Liver, only 1% energy. Muscle carbohydrate, fat, muscle fat, 5%, muscle carbohydrate, 3%. So carbohydrate storage in the body is not that much. And that's important to know. Lots of storage of chemical energy in fats. Okay, so this is going to be important when we start deciding what type of fuel to take to our top tube of the bike, for example, as I showed you in that first picture. Okay, so the amount of carbohydrate that can be stored does vary between people, and it is influenced by training. An untrained person may only be able to store about 280 grams of carbohydrate. A trained person, maybe 2 to 3 times that, 720 grams. The absolute numbers here are not critical. The concept of knowing that an untrained person has less of an ability to store carbohydrate than a trained person is important. This is influenced by diet, and you can go and look at table 3.1 in the textbook. Okay. Storage, body composition of endurance runners is lower percent body comp, so 4 to 7% possibly for endurance runners. Proteins are present in all cells. Cell walls, filaments, structural compounds. Protein storage is tightly regulated in the human body. Weightlifting does influence protein storage. Starvation leads to a reduction in protein storage. Okay, so again, the figure that Noakes has in his book was for someone with a 15% body comp. Endurance athletes may actually drop under 10%, and some of that may be unhealthy, and we need to be really careful about getting below a certain threshold of body composition, and that could actually lead to detriments in performance. And men and women have a different amount of threshold for minimum body composition. Okay, what endurance athletes want to know is how to optimize fuel storage, both in carbohydrates, well, really in carbohydrates, not really in fats. You don't really want to go around talking with people about how to optimize their fat, their adipose tissue, their body composition, their percent fat. Usually, endurance athletes are trying to figure out how to reduce that. But I'll say you really want to get that percent body comp into a manageable region. So really what athletes want to know is how to optimize fuel storage, carbohydrates, how to replenish fuel storage during a race or maybe after a training session, what to eat afterwards or what to eat after a race even, to restock or restore carbohydrates. The next section of the book looks at factors that influence storage of fuel. The emphasis is placed on storage of carbohydrates, not fat, because fat tends to be plentiful for most of us anyhow. Okay, factors that affect fuel, really carbohydrate storage. Carbohydrate storage is greater for trained versus untrained people, as I presented just a few slides ago. Endurance athletes commonly use this model of deplete carbohydrates through exercise, then eat something specifically, and then replenish the carbohydrate stores in the body, and what you're going to eat during an event after exercise will ultimately influence what your body stores. So there's this model that athletes use to deplete and then replenish, and diet is just what you're going to eat to get there. Factors affecting depletion of carbohydrate. Well, exercise intensity and duration are two factors that influence depletion of carbohydrates. The higher the intensity, the more rapid rate of glycogen use. Continuing exercise at 70 to 80% VO2 max for periods longer than 2 hours results in the greatest muscle glycogen depletion. All right, let's look at some data from that. This is figure 3.6 in your textbook. And we've got two figures here, and it's important to distinguish between these two. Figure A, the top one, is liver glycogen content. All right, so remember, there's this interplay between liver, what's stored in the liver for glycogen, and the B, the bottom graph here, is muscle glycogen. All right, this is the amount of glycogen stored in the muscle. So we've got this this repository, this storage of glucose or glycogen in the liver. The liver will release glycogen into the blood. It will be referred to as blood glucose at that point. The blood glucose is transported via the circulatory system to the muscle. And once it enters the muscle, we'll call it muscle glycogen. So remember, there's this interplay between these two graphs here. So here's liver glycogen on the y-axis, percent exercise intensity on the x-axis. So this is 85% effort, this is 75% effort, this is 70% effort. Actually, this is really time on the x-axis. These are three lines representing the intensity. So this 70% is exercise that's lasting longer. 85% is going shorter. So sorry about that. This is time on the x-axis. And this line represents exercising during a 42-kilometer marathon. That's a standard 26.2 mile marathon. This athlete's doing it at 85%. These are doing 90-kilometer Comrades Marathon. Remember, the Comrades Marathon is in South Africa. That's a double marathon. So you're going at a lower intensity. For those, it's going to take longer. The depletion of liver glycogen, it's not as much known about liver glycogen. It's a little harder to get these data. You have to do a biopsy, stick something into the liver and pulling some of the liver out. But the rate of liver glycogen depletion is dependent on intensity of exercise. Down here, muscle glycogen, this is what is in the muscle. This is muscle glycogen on the y-axis, and this is time on the x-axis, and then this is just muscle glycogen, different set of units. And then each line represents a different level of intensity of exercise. The solid lines are continuous exercise. The dashed line are intermittent exercise, so interval training. Bottom line here is if you do intermittent exercise, high intensity, 150% of VO2 max, so you're running much faster than the speed that you would elicit VO2 max at. So these are 100-meter sprints, 200-meter sprints, all right? This one's 150%. This one's 120% VO2 max. The higher the intensity of exercise, the quicker muscle glycogen is used. The quicker muscle glycogen is depleted. The lower the intensity, the slower use of muscle glycogen, the slower depletion of muscle glycogen. The greatest amount of muscle glycogen depletion happens during intermittent exercise, as well as exercise between 70 and 85% VO2 max. And you can see the time down here, that's 2 hours. This is, well, this is about 4 hours, 5 hours of exercise. All right, let me get some highlights here. Lower intensity, lower rate of liver glycogen used. Lower intensity, lower rate of muscle glycogen used. All right, and we'll talk about where the other energy is coming from for lower intensity, and that's obviously going to be fats. So just some highlights of this figure, 3.6. Less is known about liver glycogen because it's a little harder to get that. Muscle glycogen is also not easy to get, although there is new instrument coming out that we can measure muscle glycogen using ultrasound. Rate of liver glycogen is tend to be thought of as being linear, and it is dependent on intensity, and it can be depleted in about 2 to 3 hours. Muscle glycogen levels fall over time as well. Rate of depletion of muscle glycogen is initially rapid, so this is a nonlinear line here. Okay, nonlinear line. Until about 1/3 levels are reached. Rate is dependent on intensity of exercise. The rate of depletion of muscle glycogen is dependent on the intensity of exercise. Muscle glycogen can be depleted rapidly using intermittent exercise or intervals. That's the dotted lines in that plot. Continuous exercise at 70 to 85% VO2 max results in the greatest muscle glycogen depletion, and it's depleted in 2 to 4 hours. Again, depending on the type of athlete. But general rule of thumb. And that, again, that's important because if we're doing an event that's going to last 10 hours or 12 hours or 17 hours, we need to be mindful of when fuel is being depleted. Because once you don't have fuel in the body, you're done. You can't continue. It's like having an empty gas tank in a car. You can't make the car go if you don't have gas in the tank. Okay, so factors that affect food storage: diet. Eating a high carbohydrate diet does influence food storage. Glucose produced by the liver is used to return blood glucose to normal levels, and muscle glycogen stores back to normal. So remember, digestion: food goes into the stomach, into the GI, it's absorbed. Glucose is absorbed there, or glycogen. Carbohydrates are absorbed there and then transported to the liver. And the liver is then responsible for replenishing blood glucose levels, which is a circulatory system, taking glucose to the muscle to replenish the muscle glycogen. The resynthesis of glycogen is aided by a high carbohydrate diet, but athletes who think they are on a high carbohydrate diet may not actually be on a high carbohydrate diet. So there's a lot of nutrition work on understanding diets, and it is probably easier today than 5-10 years ago to track what you eat because apps on your phone are readily available. It makes it a little easier to track what your macronutrient intake is. A lot of times people may think they're on a high carbohydrate diet, but they may not actually be on that type of diet. So this leads to the question, does a pre-race carbohydrate depletion replenishing program work, and specifically carb loading? Does carb loading work? Well, let's go back and look at the original research that drove this, and Noakes does a really good job of reviewing this type of work and some of the history behind carbohydrate loading. And he's got this figure, 3.7, that is a summary of some data from a research study. On the y-axis is muscle glycogen. Okay, just muscle glycogen on this axis as well, just different ways to represent it. On the x-axis is days. Okay, day 0 is a exercise to exhaustion day. And same thing here, exercise to exhaustion day here. All right, so what we have here are 3 groups, A, B, and C. And this is a classic study in carbohydrate loading, and this study has been used to support the idea of carbohydrate loading. So let's go through each of these groups. I've got this on the next slide. Group A, exercise to exhaustion at day -3. So that's what that arrow right there represents. They ate a high-fat, high-protein, low-carbohydrate diet for 3 days. Okay. And then exercise to exhaustion again at day 0. And then ate a high carbohydrate diet for 7 days, okay, for 7 days. So carbohydrate loading. And that's group A right here. Okay, I'll go through where they ended up in just a second. Group B exercised to exhaustion at -1, then ate a high-fat diet for 1 day, did another exercise to exhaustion at day 0, and then ate a high carbohydrate diet for 7 days. That's B. And then C exercised exhaustion only at day 0, and then ate a high carbohydrate diet for 7 days. And that's group C. Okay, what are some things that we're getting from this? Well, exercise to exhaustion for A and B and C muscle glycogen was depleted on those days. Drops down, and drops down. So muscle glycogen went down, went down, went down with exercise to exhaustion. That's one thing. Another thing that we see is when you're eating a high-fat diet, you are not seeing the glycogen resynthesis. You're not seeing muscle glycogen stores increasing. Okay, this is the high-fat diet here. This high-fat diet here. She was not on a high-fat diet. So that's another thing. A third thing we're seeing is once you introduce carbohydrate into the diet, and it's a high carbohydrate diet, so 90% of the diet comes from carbohydrate, we're seeing this increase in muscle glycogen for each group, A, B, and C. One more thing we're seeing is where these groups ended up was different at day 7. Group A ended up with the highest amount of muscle glycogen, B the next highest, and C the lowest, but still higher than they began. Here's C here in the beginning, here's C at the end. All right, so let me pull some points together on this. Key points: exercise due to exhaustion, reduced muscle glycogen level, minimum glycogen resynthesis on a high-fat, high-protein diet for groups A, B. C did not do that. Muscle glycogen levels peaked for group B and continued to rise for group A. And something really important here is that the subjects in the study were relatively unfit. Okay, so A keeps going up in muscle glycogen, even at the end of the study. So we don't know what would happen after 7 days for group A. Group B plateaued and group C plateaued in muscle glycogen. Key, subjects were relatively unfit. But this is the model that was used to really promote and encourage carbohydrate loading. And carbohydrate loading consists of a depletion carbohydrate loading diet that should be similar to group A, because A had the greatest amount of muscle glycogen at the end of the 7-day period. Carbohydrate loading pre-race parties, eating a lot 1 to 2 days before an event, is not a replication of this study. In this study, to maximize the amount of muscle glycogen, the subjects that used a 7-day pre-race carbohydrate loading pattern was needed. But remember, subjects were relatively unfit. And I'm going to show you some data in just a second on data that from a fit group of subjects. Key points: different manipulations of carbohydrate fat diets can be used to maximize muscle glycogen or influence muscle glycogen. Again, A, B, and C each did increase their muscle glycogen. The main detriments of muscle glycogen levels during carbohydrate loading are the athlete's level of training and the amount of carbohydrate eaten daily. I should also point out here that another key component to these carbohydrate loading was that depletion of muscle glycogen and then eating the hard carbohydrate diet after that. And most people are not doing that in a carbohydrate loading party that you typically see people, athletes, they're organize a carb loading party prior to the event. They'll eat spaghetti or some types of pasta. No, the trick with this is to deplete and then replenish. All right, so now let's look at carb loading with trained athletes. And so here's some data from a research study. This research team had 3 groups of subjects go through depletion reloading protocols, tested muscle glycogen stores. The bottom line of this study is traditional depletion loading protocol did not offer any advantages to trained athletes. All right, that's important. Eating a high carbohydrate diet during the 3 days before competition was critical. Let's see. Let me just change this. Okay, here's their data. All right, muscle glycogen on the y-axis, days that they're testing the subjects on the x-axis, and again, just muscle glycogen on the other y-axis, just different set of units. 21 kilometer run here, that's a half marathon, 13.1 miles, and a 21 kilometer race over here. And we've got 3 groups again, A, B, and C. All right. they ran all ran the 21-kilometer race here at day 1. And then group A ate 15% carbohydrate diet for 4 days, and then they ate 75% carbohydrate diet after that. Group C was 50% carbohydrate and then 75% carbohydrate. Group B was 50%, 50%. All right, so this is just summarizing that. 15% carbohydrate for 3 days. I said 4, but it's 3. 75% carbohydrates for 3. 50% carbohydrate throughout the duration of the 7 days, and 50-75 for Group C. 5 days of tapered running at 75% VO2 max, and 1 day of rest. This was just their exercise protocol prior to doing this study. Groups A, okay, here's some important parts now. Group A and C reached the same levels of muscle glycogen. Groups A and C reached the same levels of muscle glycogen. Bottom line of that is eat a high carbohydrate diet for at least 3 days pre-race. Okay, eat a high carbohydrate diet at least 3 days pre-race. That's what that message would tell us. Extended muscle glycogen after a 21-kilometer race was the same for each group, okay, after the race. So they all dropped down to the same levels. This is really important. No difference in race performance between the 3 groups. So none of the groups had an advantage based upon their diet in this 7-day period and the taper that they followed. There was no advantage for one group over the other. Carbohydrate loading may not be as effective for trained versus untrained athletes. Okay, so got to keep this in mind when you're talking with athletes, or if you're doing an event, that there may not be any advantage to carbohydrate loading. What athletes talk about, especially for endurance events that are lasting 8, 9, 10, 12, 15 hours, is to maintain your regular diet through the week prior to the event. Don't manipulate your diet during that week. Stay with your regular diet, and then have a good plan during the race to replenish and take in fuels that you need to complete the event. Okay, so that's just a quick summary of part 2, storage of fats. We talked about that, glucose, and this interplay of liver storage and muscle storage. And the blood glucose is the transport of glucose from the liver to the muscle. And then we talked about carbohydrate loading. And a key for endurance athletes is to maintain a regular diet going into their endurance event the week before. Okay, thanks everybody.